Watch this ball. It goes up, curves over, and comes down. Simple, right? But hidden inside that curve is an equation, and not an ordinary one. It has an x squared in it. And that one little square changes everything, because this equation doesn't just describe the path. It knows the exact spot where the ball will land before it ever gets there. By the end of this video, so will you. Welcome to Chapter 4, Quadratic Equations. Here's the difference. A linear equation gives you a straight line. The moment you add an x squared, that line bends into a curve, a parabola. That's a quadratic. And every quadratic can be written in one tidy form, ax squared plus bx plus c equals 0. The only rule. A cannot be 0, because if it were, the x squared would vanish and we would be straight back to a boring line. The x squared is the star of this chapter. So here's the plan. First, we'll turn real situations into quadratic equations. Then we'll solve them two ways, by factorizing, and with a formula that never fails. And finally, a neat trick that tells you how many answers to expect before you solve a single thing. Let's build one. Picture a rectangular garden. We don't know its size yet, so call the width x. The owner tells us just one thing, it's 3 meters longer than it is wide. So the length is x plus 3. And the whole garden covers 40 square meters. Area is length times width, so x times x plus 3 equals 40. Open the bracket, bring everything to one side, and look what appears, x squared plus 3x minus 40 equals 0. A quadratic, born from a garden. Now, can we find the sides? Here's the idea behind factorizing. Split the middle. We need two numbers that multiply to minus 40 and add up to plus 3. Think. 8 and minus 5. 8 times minus 5 is minus 40. 8 plus minus 5 is 3. Perfect. So the equation becomes x plus 8 times x minus 5 equals 0. And here's the magic, if two things multiply to give 0, one of them must be 0. So x is minus 8 or x is 5. A garden can't have a width of minus 8 meters, so we throw that one away. The width is 5, the length is 8. 5 times 8, 40. The garden checks out. There's a third way to solve a quadratic, and it's the prettiest because you can literally see it. Take x squared plus 6x plus 5 equals 0. Move the 5 across, x squared plus 6x equals minus 5. Now picture x squared as a square with side x. The 6x. Split it in two, 3x and 3x, and lay a strip on each side. You've almost built a bigger square, but there's a corner missing, a 3 by 3 gap. So we fill it. Add 9 to complete the square, to both sides, to keep things fair. The left side is now a perfect square, x plus 3, all squared. The right side is 4. Take the square root, x plus 3 is plus or minus 2. So x is minus 1 or minus 5. We completed the square, and the answer simply fell out. Now here's the beautiful shortcut. Do that exact same completing the square trick, not on numbers, but on the general quadratic, ax squared plus bx plus c equals 0, and out drops a formula that works for every quadratic, forever. This is it. X equals minus b, plus or minus the square root of b squared minus 4ac, all over 2a. Learn the shape of it, and no quadratic can hide from you. Let's put it to work. A bus covers 90 kilometers. The driver says, if I'd gone just 15 kilometers an hour faster, I'd have arrived a whole hour earlier. A small change in speed, an entire hour saved. What speed was the bus going? Time is distance over speed. At speed x, the trip takes 90 over x, 15 faster, 90 over x plus 15. The difference is exactly 1 hour. Tidy it up and you get x squared plus 15x minus 1350 equals 0. This one won't factor neatly, so the formula R is 1, B is 15, C is minus 1350. Under the root, 5625, whose square root is a clean 75. So x is minus 15 plus or minus 75 over 2, 30 or minus 45. A bus can't go minus 45, so the speed was 30 kilometers an hour. Now here's the clever part. See that p's under the square root, b squared minus 4ac. It has a name, the discriminant. And on its own, before you finish solving, it tells you the whole story. If it's positive, the square root is real and you get two different answers, the parabola cuts the axis into places. If it's exactly 0, the plus or minus disappears, both answers merge into one, and the parabola just kisses the axis. And if it's negative, you can't take the square root of a negative, so there are no real answers at all, the parabola floats above the axis, never touching. One little number, three different words. Let's read a few at a glance. X squared minus 4x plus 4, the discriminant is 0, so one repeated root. X squared plus x plus 1 minus 3, negative, so no real roots. X squared minus 5x plus 6, positive, two neat roots. You didn't fully solve a single one, yet you already know exactly what to expect. That's the power of the discriminant. One more, because this one hides everywhere, gardens, swimming pools, even photo frames. A lawn, 20 meters by 15, has a path of the same width running all the way around it. Call that width x, step outside the lawn, and the whole thing becomes 20 plus 2x by 15 plus 2x, because the path adds x on each side. The path's area is the big rectangle minus the lawn. Set that equal to the area we are given, simplify, and once again, a quadratic. Solve it, throw away the impossible answer, and the path turns out to be 3 meters wide. Same tool, brand new disguise. So here's the whole chapter in 3 moves. 1. Turn the situation into ax squared plus bx plus c equals 0. 2. Solve it by factorizing when it's friendly, or with the formula when it's not. 3. Let the discriminant tell you in advance how many real answers to expect. Gardens, journeys, borders, all the same maths underneath. If a quadratic finally makes sense now, give this a like, share it with someone who's stuck on it, and subscribe. Next up is Chapter 5, Arithmetic Progressions. Free notes, quizzes and practice are waiting at schoolrevise.com. Revise. Practice. Excel. See you in the next one.